All right, chapter 3 is numbers in the real world, and section 3A is uses and abuses of percentages. So we'll talk about absolute change and relative change, or absolute change and percentage change. Before we get started, we just have to review some basics of percentages. Converting a fraction to a percentage is a matter of, well, one nice trick is that the fraction 51 is divided by 100. 51 over 100, that's 51 per 100. If you think of the word percent, per means to divide, cent is Latin for 100, so 51 per 100 is literally 51%. So that's a nice start, a nice connection to make when we deal with percentages. Now next up, 1 over 50, so it's not per 100 anymore, so we'll convert it to a decimal. Calculator does a good job of this, giving us 0.02. Now, to translate the decimal to a percentage, remember that we need to step 1, 2 decimals to the right, so 1, 2, to make that 2% and put a percent sign. Similarly for 3/8, calculator tells us that 3/8 is equal to 0.375 as a decimal. Once again, we move this decimal place 1 and then 2 places to get 37.5%. Okay, similarly going the other way, if we have 62%, that's literally 62 per 100, or 62 divided by 100. Simplifying that fraction, we get 31 out of 50, or 31 over 50. Similarly for 3%, 3 per 100, 3 divided by 100. This fraction doesn't simplify, so we're all done. 120% divided by, 120% is 120 per 100. Well, divided by 100, that is. So simplifying, canceling common factors of 10, we get 12 over 10. Canceling common factors of 2, we get 6 over 5. And that's our final answer there, 6 over 5, or 6/5. Could be 1 and 1/5 if they want a mixed fraction, but an improper fraction is probably just fine. So let's see. Now to deal with tax amounts. So just getting, using percentages in a way that we're used to, or rates in a way that we're used to. We of course know that the sales tax amount is equal to the tax rate times the cost of the item. So in the example we're given below, they say a book costs $12.95. Its sales tax rate is 9%. How much tax is paid on this $12.95 book? Okay, we take the rate, 0.09 times $12.95. Remember to always convert percentages to decimals before we put them into formulas. That's always going to be the case. We'll always have to do that, or else we'll be off by a factor of 100. And we get a number like this from a calculator, and then we round that to the nearest cent because it's reasonable since we're working with dollars. And we say the tax amount is $1.17. Now, what's the total cost of the book? Well, the total cost is the price of the book plus taxes. We're all familiar with this type of situation. So we have the price of this book plus the taxes, and we put that together at $14.12. Now, what I've done off to the side, there's an alternate calculation that we can see here. So to calculate this $1.17, it was really 0.09 times 12.95. So this is 0.09 times 12.95 right here. We also added to that 12.95, and this is our 12.95 right here. So if we were to just multiply this number 12.95 times 1 plus 0.09, this would be the price plus the 9% tax rate of this. We'd have the same value right here. So really, if we multiply by 1.09, it's a way to think about what we would end up with. It would be this percent increase up to $14.12. Now, we don't need to do this problem this way. It's just nice to see this 1 plus situation showing up. Now, when we look at other rates later, we'll use this idea a little bit further. So similar to sales tax is a discount amount. If we have a discount rate times an original price, that's the amount off of an item, right? The amount that we're going to discount from the price of an item. So an item costs $380. It's on sale for 35% off its price. Okay, first thing we'll do, convert 35% to a decimal, 0.35. Very good. Now we'll multiply the rate, discount rate, times the full price, and that gives us $133. That's our discount amount. That's the amount we'll take off the price. So we know that the total price, or the sale price, is the original price minus the discount amount, this being the discount amount. And that's 380 minus 133 to get $247. Now again, off to the right, we've made this alternate calculation. So again, here's 380 times 1. That makes up this component of this calculation. And then we're subtracting 0.35 times 380, which is this $133. So this piece and this piece times each other gives us 133. And we're subtracting that from 380. And that, of course, will also give us 247. So if we multiplied $380 times 0.65, we'd get $247. Now what that's also telling us, this number off to the right there, the 1 minus 0.35, we use minus 0.35 because it's an amount off, it's a discount amount. But something this is telling us, this value here is 0.65. What we're actually paying for the item is 65% of its actual value, of its original price. So it's another way of thinking about this. Of course, we don't need to solve this problem using this alternate calculation, but seeing that that's in the background is useful for later. Percent change and absolute change. So percent change is the same as relative change. I'll make a note of that here. This is also relative change. You'll see that word sometimes, relative increase or relative decrease. Now, first though, percent change, or sorry, absolute change is a new value minus an original value. So if we started with some original value or original price, then to get the absolute change, we'd do the new price or the new value minus the original value. Okay, that's a straightforward calculation. It could be positive, it could be negative based on whether or not the new value is larger or less than the original value. Now for the percent change is the absolute change, so this calculation up here, divided by the original amount or the original value. What I'll often use in this situation is new for new value and old for original value. So what we'll often see here is maybe expanding this formula a little further. We'll see it as new minus old over old. You will note that old is original value, and another word to use too is maybe an initial value, but even better is the reference value. Okay, the reference value meaning, you know, what it started with or what we're basing things off of. So we'll keep these terms in mind for future problems. Okay, so if this number comes out to a negative, then this is a relative decrease. If it comes out to a positive, it's a relative increase. Okay, so let's look at an example below and see this thing in action. A jacket usually sells for $135. It's now on sale for $60.75. Find the percent decrease of the sale price from the usual price. In other words, find the percentage off of the regular price that this sale price is. Okay, so we take, to find the relative change, we'll do new minus old over old, or the new value minus the original value divided by the original value. $60.75 minus $135, which, by the way, this line is the absolute change in case they were asking for that. And then we divide by the old value or the original value of $135. What we arrive at is negative 0.55. We convert it to a percentage, moving the decimal place 1, then 2 places. So we have negative 55%. Since that number is negative, we know that this is a 55% decrease, or it's 55% off. In other words, we're paying 45% of the full price for this jacket after the sale, after the discount amount is taken off. Okay, so let's see something that might be a little bit trickier here. So suppose we have two tablets, tablet A and tablet B. A costs $400, B costs $500. So first they ask us, what is the difference in the price of these two? They're not saying the absolute difference, because neither one of those is necessarily a reference value in this given statement. So the difference in price, if we're not told to find the absolute change, we just take the larger minus the smaller, and we see that there's a $100 difference. Tablet A is $100 less than tablet B. This sums up with that $100 in our answer above means, and a nice sentence here. Probably one of the best ways to relate this information. So we've got that. That's not very difficult. Now, in terms of a relative difference or relative change, how much more is tablet B's price than tablet A's price? And this is a tricky problem. Relatively, as a relative difference, how much more is tablet B's price than tablet A's price? So the question is this: the relative change we know is new minus old over old. So let me ask, which of these is the new value and which one is the old value? We look at the language of this. It's saying, how much more is tablet B than tablet A? We're comparing tablet B's price to tablet A's price. So we're using tablet A's price as a reference value. So remember, reference value is the old value. Another way to see this is to say, whatever one is after the word than is the old value, and whatever one's before the word than is the new value. So if we want to just use a quick and easy rule, that will probably always work for us. So the relative change now is B's price, new minus old over old. This is A's price as the old price in both places. So we have $100 over $400. That comes out to 0.25 or 25%. So then we note it's positive. So tablet B is 25% more than tablet A in terms of price. Okay. Now, the second question, or the third question rather, the one after this one, is how much less is tablet A's price than tablet B's price as a relative difference? Now, don't make this mistake. Just because B is 25% more than A does not mean that A is 25% less than B. This is one of our first possible mistakes or abuses we can make with a percentage. Okay, let's calculate it exactly and see what the case is. So in this case, tablet A's price is being compared to tablet B's price, or A is before the word than, and B is after the word than. So we put old after than and new before. We want to mark it that way. B is the reference value in this case. So new minus old over old, this formula here. A being the old price, or the new price, B being the reference or the old value. Is this, we have negative 100 over $500. The dollars cancel. We didn't actually need to put them into the problem, but it's good to see them cancel. We have negative 0.2. That's negative 20% as a percentage, which means that this is a relative decrease. So A is 20% less than tablet B. Okay, note that A is not 25% less than tablet B. This is relative to whatever price or value we're using as our reference value. And the key thing is this $400 is different than this $500 because up here, A is the reference, and down here, B is the reference value. So relative to is the phrase to think of in this situation. So that's uncovering one possible mistake or abuse we can make with percentages. Let's get a little bit deeper into this. So suppose our job, we just took a new job. It adds a 5% raise to your salary each year. What is the relative change in your salary at the end of 4 years of working at that job? So we're going to get 5% raise at the end of each year. And at the end of year 4, what is the relative change in our salary? In other words, what's our salary going to be going into year 5? Okay, well, it seems like, one possible answer we could say is that, well, it's 20%, and we'd be wrong. We would be wrong because each year we get 5% raise on the previous year's raise. So after year 1, when we make a $5,000, when we get a 5% raise, the raise at the end of year 2 is going to be a raise on our original salary and the 5% that was added in year 1. So there's a compounding effect, just like a compound interest account. So in order to calculate this, we just choose a salary. We say, maybe we'll set our salary at $100,000. A number with a lot of zeros, well, that's nice because it's a good salary, but it's also nice because we won't have as many decimals to deal with as we compute 5% increases of this number over and over again. So choose something with a lot of zeros. Give yourself a $1 million salary if you'd like to. You could come out with the same values that we'll come out with in this situation. And we'll make a table here of year, salary, and then the raise at the end of that year. So we need to go all the way down to year 5 and get our salary for the 5th year. Okay, that's at the end of year 4. So year 1, we're paid $100,000. At the end of that year, we're going to get a 5% raise. So $100,000 times 0.05, converting 5% to 0.05 to a decimal, as we always should. And that's going to be a $5,000 raise. We add that $5,000 to $100,000, we have $105,000. So that's our salary for year 2. Now at the end of year 2, we have $105,000. To get our raise at the end of year 2, we multiply it by 0.05, our 5%, and we have a raise of $5,250. Now we add $5,250 to $105,000 to get our salary for year 3. That's this number here. Now, our raise at the end of year 3 is this value times 0.05 once again, and we get $5,512.50. And now we add that to this number to get our salary for year 4. Okay, we're almost there. We repeat that method one more time. The work's not shown just to free up a little space, but this number times 0.05 once again to get our raise amount. Then we add that back to this number, and we should end up with $121,550.625. So we'll round that number to 63 cents. We don't have to, but it's nice to do so in this case. We typically shouldn't round our values until we get to our final answer, but this is so far along in our decimals that it won't matter very much. Now, this is our raise at the end of year 4 with 4 consecutive 5% raises. Okay, now what's the relative change from this number back to our original salary? So in other words, this is the new and this is the old. Okay, so we have new minus old over old. It's 121,000 minus 100,000 over 100,000. That leaves us with $21,550.63 over $100,000. And then dividing that out, we get 0.21555063. We'll convert that to a percentage, and we'll even round it to the nearest hundredth of a percent to get 21.55%. This number is positive, so this is an increase. So our salary increases by 21.55%. That's exactly what we should have expected. We knew it should have been more than 20% because those raises are compound. It's a raise on a raise. So we're going to have more than 5% times 4. It is close, but as time goes on, this number would get even further from what we would approximate with numbers like these. Okay, so if we were to be there 10 years, we'd be much further above a 50% raise than the 21.55% is above a 20% raise. So percentages never add, right? That's the key here. 5% added to itself 4 times would have been 20%. That is not the increase that we end up with. We cannot add percentages or rates like this. Okay, let's do a similar problem to this. And then I'll come back to using an alternative method to calculate this. And we're going to see that 1 plus a rate or 1 plus a number show up when we do that. So below, we have a certain stock has lost 10% of its value by the end of January 1st, or by the end of January. So it started at some amount in January. By the end of the month, it lost 10% of its value. Then it gained 4% by the end of February, so over the month of February. And then it gained 6% over the month of March, okay? Has this stock regained all of its value? One month it lost 10%, another month it gained 4%, another month it gained 6%. Well, we know enough by now not to say, yes, it has regained its value. Something must be up with this. Okay, let's find out what that is. So if it hasn't regained its full value that it started with on January 1st, let's find out what percentage it's increased or decreased overall. So we'll do the same, we'll do something very similar. We'll set an initial value of our stock. On January 1st, we'll make a table of dates and then the value of the stock. So we know that the stock starts out on January 1st. We'll just say it's worth $100 per share. It's a reasonable way to do this. Now, by the end of January, on January 31st, it's lost 10% of its value. So $100 minus 10% of 100, or 0.1 times $100. I'm adding an extra line here just to see it. Note that 100 minus 0.1 times 100 is 100 times 1 minus 0.1. Here's 100 times 1, and then here's negative 0.1 times 100 with this part and this part respectively. Okay, so we're seeing our 1 plus or 1 minus trick showing up again. Okay, we want to keep an eye on that, because if we do this, we'll realize that $100 minus $10 is $90, or we can do it this way and realize that $100 times 0.9 is $90. Either way, we arrive at the same place. Now it's important to see how this works. We don't have to do both ways, but seeing both ways is crucial for the rest of this. Now, we've got, by the end of February, we start the month at $90. By the end of February, it gains 4%, so plus 0.04 of its value starting in February. And now we see why it's not going to regain everything, because if we look at this, again, rewriting it as $90 times 1 plus 0.04. Here's the 90. Here's the 0.04 times 90. And doing this either way, either coming out with $90 plus $3.60 or 90 times 1.04, we're going to arrive at this answer no matter what, 93.60. Okay, so we have 93.60 at the end of February. So going into March, the stock is worth $93.60. By the end of March, it will gain 6% of its value. So 6% times 93.60. And again, we can write this as 93 times 1.06, and this is the 0.06 times 93 component. Okay. And doing this either way, it's good for the reader or the viewer to check both ways to see that they get the same answer. Do it this way and see that that comes out to the same value as this way, and both are $99.216. Now we'll round that just to be reasonable to $99.22 or $99.22. And then we realized that, yeah, by the end of March, we did not regain our value back to $100. Okay, in fact, we're just a little bit short. So the relative change is this new value of $99.22 minus the old value of 100 divided by the old value of 100. This comes out to negative 0.78 over 100. And a quick way to see that is a number divided by 100 is that number per 100 or percent. Okay, so we can convert that pretty quickly to a percentage. It's negative 78%. So what we realize is this was a relative decrease of 0.78%. So our stock's value actually decreased by 0.78% from January 1st to March 31st. And that's what we would expect. Again, the 10% loss is on $100, but when it makes a gain of 4% back, it doesn't make that gain on $100, it makes it on $90, its current value. And that's where things go wrong. We only earn back $3.60, not the full $4 that would combine with a full $6 down here, which doesn't happen either, to give us back $100 in full. Again, it's close, but the more percentages that are involved, the more months that would go by, the further off such an approximation would be. Okay, so let's see it, in both these problems, we made up numbers, right? So it must be that it doesn't matter what number we start with. And in fact, that's true. And furthermore, we can use a 1 plus trick, okay? So let's go to the alternate method for this most recent problem first and say, okay, at the end of January, the month of January, the stock is 90% of its original value. In other words, 1 minus 0.1, and then times the stock is 104% of its value over that month, 1 plus 0.04, times 1.06, which is 106% of its value over that month, to get this. So in other words, take each of your percentages, do 1 minus for a decrease and 1 plus for an increase, and you form these three numbers here, these three here, multiply them together. What do we arrive at? 0.99216. Okay, so we're just using our rates to see what we end up with. Our relative change, well, there's an understood 1 out here, if we need to think of it this way. We're just saying that our stock was worth $1 per share in this case. This is our shortcut or alternative method, so we'll just always have that be a 1. And then the relative change in this case is new minus old, and we haven't written this in, but it's divided by old, which is 1, but since it's dividing by 1, it doesn't change anything, so we don't really need to write it. And we arrive at the same exact thing, negative 0.0078, which is negative 0.78%. So we didn't need a value to start with overall. And in fact, this method is a really nice shortcut to doing a problem like this, okay? And especially if we're going to do a problem like 0.7 above and take it out to many, many years. We don't want to do 10 years worth of working at this job again, 5% raises each year, and have to do 10 rows in a table. So here's the trick. What we realize is that we started with $100,000. Okay, to go back to this, this is an alternative method for this one. To get our salary for the second year, we do 1 times 100,000, which covers our $100,000, plus our raise of 5% of $100. Okay, so that's 1.05 times 100,000. The reader can check right here. Make sure that 100,000 times 1.05 is $105,000. That was our salary for the second year. Well, what do we do for the third year? Well, we do 1 times all of our second year's salary plus 0.5 times all of our second year's salary. So again, we increase that whole salary by 5%. So again, though, we're just multiplying by 1.05. Now what the reader can do is do 100,000 times 1.05 times 1.05 and see that that matches our third year salary. Okay, and this continues. If we're going to do 4 of these raises, here's the first raise, second raise, third raise, fourth raise, or second year salary, third year, fourth year, fifth year salary. And really, a shortcut in all of this is we could just say 100,000 times 1.05 to the 4th power. And that would give us the number we have off to the side. That's a really handy thing to have around. So the key is this. That exponent of 4th power right here for 1.05, since each year's raise is the same every time. Okay? Now, we really don't even need this $100,000. Just like we saw in the example that we just looked at before this one, there's an understood 1 right here. We're just saying that our salary now is worth $1, and we're going to get 4 consecutive raises of 5%. So that's 1 plus 0.05, and we raise it to the 4th power. Since 4 years are going to go by, we're going to multiply by 1.05 4 times. And what's the result of that? We get this number, which should look fairly familiar thanks to this. Only it's off by a factor of 1 million, or 100,000, which is not a big deal. And what we arrive at is we'll take this is our new value, minus our old value, which is 1. So new minus old here, divided by old. And well, Really dividing by 1 isn't a big deal, doesn't change much, but it's good to have seen it. And what we arrive at is 0.215500625, and rounding that to 2 decimal places, or sorry, converting that to a percentage and rounding to the nearest hundredth of a percent leaves us with 21.55%. It's positive, so that's an increase, and that's exactly what we had before. So it turns out we didn't need to make up a salary. This was used to convince us that we could just use this trick instead, and really the key to all of this is just doing this. 1 plus your rate was 0.05, raised to the number of years or the number of times we're going to apply that rate. And that's it. That's all we have to do, other than the relative change, is to subtract 1 and convert to a decimal. Okay, so that's a nice little shortcut. And what I'll do is leave the reader with this exercise here. Do example 0.14. We see in this case, we have a house. The value of it is increasing by 2% each year. What is the relative change in your house's value at the end of 10 years? Note that the rate is 2%, and the number of times that's going to happen is 10. So model the problem that we just did, or you model this problem after the one that we just looked at, the salary or raise problem, without doing the long way, or you can do the long way as well just to check. Okay, so that's it for section 3.A. Certainly have a look at all the extra problems in this section at the end, but number 14 down there is most important. And good luck with these.